All right, let's have just kind of a quick review here of what we talked about on Friday with predicting the products of a reaction. Okay, the first step in predicting the products of a reaction are to, or is to, right, find out what kind of reaction it is. Once we know what kind of reaction it is, then we know what the pattern we have to follow is, and we simply follow that pattern. Okay, once we've followed that pattern, we check drops and swaps on ionic compounds in the products. Okay, we check for special elements in the products, and we're done, unless it's a combustion reaction, and then it's different balancing rules, right? But for number one here, it says potassium is added to water, right? So there's actually two ways this reaction could go. I could say that it's K plus H2O, or I could say it's K plus HOH. And believe it or not, these actually will produce slightly different products. Okay, and either one would be right because they both kind of happen anyway. All right, if I'm looking at either one of these, what kind of reaction am I looking at? It's single replacement. I have an element reacting with a compound. All right. This here would be kind of like the less likely scenario, simply because I've written H2O as a molecular element or a molecular compound, whereas here I've written it as an ionic compound. Okay, and remember that replacement reactions only happen in ionic compounds. All right, or with ionic compounds. So we'll start with this one here. Okay, if K is going to be in a single replacement reaction, what part of water is it going to replace? Hydrogen, because hydrogen's listed first, it's acting as a metal, right? That means that K will end up with oxygen and hydrogen will end up by itself. Now I have to check for things once I've done that. So this is I figured out what kind of reaction type it was. I followed the pattern. Now that I've followed the pattern, okay, of a single replacement reaction, I need to check the drops and swaps that I've done. This is obviously not right because potassium's a +1 and oxygen's a -2, okay? So this should be K2O, right? Is hydrogen special when it's by itself? Yes, it is. So it should be H2. All right, now that I've done that, what do I have to do last? I have to balance the chemical reaction. And I think a 2 right here will pretty much take care of that. Everybody all right with that one? Okay. If I wrote it this way as HOH, okay, then who does K end up with? OH, right? So I get KOH, okay, and hydrogen. Okay, it's still hydrogen gas, so I still need an H2 there, right? Then I've got to come back and I've got to balance everything. So I would need a 2 here, and I would need a 2 there, and a 2 there. Okay, so the big thing here, guys, is that we have to follow the rules. That's why I gave you that flow chart on Friday. Now, I don't want the flow chart to become a crutch. Okay, you're not going to get to use the flow chart on a unit exam or anything like that. It's just there to help you kind of get the hang of it, and you should wean yourself off of it as quickly as possible. If you never need it, awesome. Okay, if you need it for a couple of days, that's fine too. All right, let's look at 4. Okay, we can look at 4. So I got magnesium solid, which is just Mg, and it's reacting with nitrogen gas. Is that special? Yes, it is. All right. What kind of reaction starts with two elements reacting with each other? Synthesis reaction. Okay, so that means I've got to have Mg with N. This is a -3, and this is a +2. So we're going to have Mg3, N2, okay, when we drop and swap that. And now I need to balance the whole reaction. Should be good there. Okay. It's going to take a little practice, but don't worry. We got lots of time. Unit exams not till October the 4th. Okay. We only have one other thing other than reactions to go over. Okay. All right. Keep working on that. I'll go through a few more in a little bit. Okay, so looking at number 10, we've got copper 1 sulfide. Okay, so important thing here is that we use the copper with the 1+ charge. Sulfide is -2. This copper is +1, so we're looking at Cu2S. Okay, it's reacting with oxygen. Is oxygen special? Yep. Okay, and it's forming copper 1 oxide, so we don't even have to predict this one. It's actually telling us what the products are. Cu2O, okay, because sulfur and oxygen have the same charges, okay, plus sulfur. And what does sulfur come as when it's by itself? Where do you see? Oh, and sulfur dioxide, sorry, SO2. Okay, so here's what we got. We got lots of oxygens on one side and less on the other. We have 3, in fact, on the product side, and we only have 2 on this side. So we have what we sometimes call the odd-even problem. Okay, what's the quickest way to make an odd number even? Times it by 2. All right, so on this side over here, I am going to multiply this side by 2. Okay, now I have an even number of oxygens on both sides. Okay, so when I do this, it gives me 4 copper. So I got to go back over here and make sure I've got 4 copper. Okay, I'm going to have now 4 oxygens. So if I put a 2 here, my oxygens will be balanced. Okay, now it's going to throw this off though. This is why we usually balance oxygen last. So I'm going to erase this 2 because I see that as soon as I balance my sulfur, my oxygen will be out of balance again. Okay, so I'm going to put a 2 here. That makes sure that I've got the 2 sulfurs. Now I have 2 times 4 is 6 plus 2 more. Sorry, 2 times 4 is 4. 2 times 4. 2 times 2 is 4. Blah, Monday morning. Okay, 2 times 2 is 4 plus 2 more is 6. A 3 here will make that work. Okay, everybody with me? So if you have that problem, if you run into that problem, on one side you've got like oxygen or sulfur or something like that in 2 places, and it's an odd number, double the one that's odd. Okay, then you'll have an even number. It'll be easier to balance. And oxygen, we usually try to balance last because it always throws everything off, especially if it's in 2 places like it was here. All right, so that's a tricky one. Any others? Try. 6. Okay. Okay, molybdenum sulfide. Okay, so here's the thing with this question. What do we have to do to ionic compounds when we drop and swap them if we can? Reduce always to the lowest form, and that's what gets people on this one. Okay, so molybdenum is MO, okay, and it's molybdenum sulfide. Now, molybdenum's charge is 6. Okay, so this is a +6, and this is a -2. So when I do this, I get 2 and 6, which I can reduce to 1 and 3. Okay, so I've got MOS3, and it's reacting with oxygen gas, which is O2. Okay, what kind of reaction is that? Single replacement. Okay, I've got an element, in this case a non-metal, reacting with the ionic compound. So molybdenum's new partner will be oxygen, and sulfur will end up by itself. So we have Mu and S. All right, but we have to do a drop and swap still. Okay, this is a +6, this is a -2, so I'm going to have the same problem I had on that side. I'll have to reduce to 1 and 3. Okay, and sulfur comes as an 8. Okay, everyone, so I followed the pattern. I've done my drops and swaps, checked for special elements. Now I need to balance the reaction. All right, so I'm going to start with the largest number, 8. I'm going to come back over here. What's the lowest common multiple of 3 and 8? 24. All right, it's not great, but that's what we'll have to do. Okay, so I'm going to put 8 times 3 is 24. That gives me 8 molybdenum. So I'm going to put an 8 here. Okay, that gives me 8 molybdenums and 24 oxygens. A 12 here will take care of my oxygens, and then I'm good. Number 7. Okay, so a similar thing here. We have molybdenum oxide, and we already know what that is from the previous question. So MOO3. Oh, yes, sorry. Good eye. Got ahead of myself. Okay, reacts with hydrogen gas, which is also a special element, H2. Okay, so in this case, with hydrogen by itself, okay, it's tricky because is it a metal or is it a non-metal? Okay, when it's by itself. All right, the answer is that it is actually going to behave as a metal by itself. But I would actually write this, I would give you the answer as being correct in either case. If you treat it as a non-metal and it's switched with oxygen, okay, there's really nothing wrong with doing that either. Okay, in all likelihood though, hydrogen would act as a metal here and it would replace molybdenum. All right, so we would have H with O and we would have molybdenum on its own. Okay, when we have this stuff together, obviously it goes like this, H2O, okay, molybdenum ends up by itself. So I would need to balance my oxygens, okay, and my molybdenums are good, and I need 3 here. Okay, and then I'd be all right. Okay. Any other ones giving us trouble? 12? Okay, so I have aluminum reacts with iodine. Is iodine special? Whoops, that's 11. As you can see, I have not finished my coffee yet. Okay, silver nitrate. Okay, that's AgNO3. Okay, that's a -1, that's a +1, so that one's balanced or swaps and drop correctly. With copper 2 chloride, Cu 2+. Okay, chlorine 1-, so we're looking at CuCl2. All right, what kind of reaction is that? Double replacement. They're both ionic compounds. That means we swap the partners. So silver will end up with chlorine, and copper will end up with nitrate. Okay, on this side, copper was a 2+, so it's also a 2+ over here, which means I'll need to do this. Okay, put the nitrate in brackets and 2 outside. Okay, this is a -1, that's a +1, so that one's okay, swapped and dropped the way it is. Once I've checked my swaps and drops, now I balance the whole reaction. So I can start with chlorine if I want. There's 2 on this side, but only 1 over here. So I'm going to put a 2 there. That gives me 2 silvers. I put a 2 there. That balances my silvers and my nitrates. And there's 1 copper on both sides. So now we're good. Okay. So the trick there is make sure you have the polyatomic ion in brackets. 13 as well? Okay. So we got barium chloride. Okay, and we have ammonium carbonate. Now, barium's a +2. That's right, right? This is BaCl2. Okay, ammonium, NH4 with carbonate, CO3. This is a -2, and that's a +1. So we'll have to put this in brackets. I'm sorry, the other way around. Drop and swap. 2 there, CO3. Okay, which one of those polyatomic ions is acting as the metal, ammonium or carbonate? Ammonium, it's positively charged and listed first. Okay, so this behaves as a metal. That means it's going to switch places with barium. So barium will end up with carbonate. This is a -2, that's a +2, so that compound is okay the way I have it written. Okay, and then ammonium is going to end up with chlorine. Okay, like so, -1, +1, so I don't have to put any brackets. It's already correct the way I've written it. Everybody with me there? Okay, so now I have to balance the whole reaction. And chlorine and ammonium are both 2's on the reactant side, which means that a 2 here will balance the whole reaction. All right. Starting to make a bit of sense? It's going to go slow at first, okay? But you get the hang of it. It's always the same steps. That's the good news, right? I write the reactants, I pick the reaction type, I follow the pattern, look for special elements, swap and drop, balance the reaction, done. Okay? It's always going to be the same steps. All right, have you keep going on that, okay? So if you get done that one, there's more reaction practice underneath there. Okay? So these ones are a little bit easier because they're already predicted for you, but there are some prediction ones underneath there. Okay, starting on number 9. So. Okay, so for number 18, okay, we got zinc bromide, so Zn with Br. Zinc is a +2 and bromine is a -1, so we're looking at ZnBr2, okay? And then it is mixed with silver nitrate solution, AgNO3, okay? That's balanced already, or swapped and dropped correctly, -1 and +1. What kind of reaction is that? Double replacement reaction. All right, so we're going to switch the metals. So zinc is going to end up with nitrate. Okay, again, zinc is a +2, so we'll need brackets and a 2 outside the brackets to swap and drop that one. And then silver will end up with bromine. -1 +1, so that's dropped and swapped correctly as well. I'm going to start balancing with the nitrates. I'm going to put a 2 here in front of silver nitrate to balance them. That will give me 2 silvers, which I have to balance on the product side over there. That gives me 2 bromines. I got 2 bromines over here, 1 zinc, 1 zinc, so we're good. Okay. Any other ones? Okay, that's right. So I'm trying to. Okay, so where do we see that one? 16? Okay, with iron salt. So that's a valid question, and we haven't gone over that. So let's just go over 16 first. So we got copper 2 sulfate. Okay, so that's going to be CuSO4. That's a -2. That's a +2. Reacts with iron solid. So the question is, how do I know on this side what charge to use for iron? Because I wasn't told. It doesn't have a charge on this side. It's an element. Okay, the answer is you go with the first one listed. Okay, and it doesn't happen very often, but once in a while you run into this situation where you don't know which one it is. In actual fact, one is far more common than the other, and so they're listed from left to right, from most common to least common. So Fe2, I think, is the most common. 3? 3 is the most common? Okay, so Fe3 is the most common, so we would go then with, all right, so iron is going to end up with sulfate. Okay, FeSO4 +3 is the most common charge for iron. -2 is always the charge on sulfate. So we will have Fe2SO4 3. Okay, and then we'll have copper by itself, and then we'll have to go back and balance everything. So we'll need 3 sulfates over here, 3 copper here, and 2 iron here. So the answer to that question is if you aren't told the charge, and it does happen when you have a multivalent metal reacting as an element, okay, then you go with the most common charge on the other side. Most of the time, you know what it is because it's already in a compound and you can figure it out. But in that case, you go with the most common. All right, any other ones? Okay, take about a 3-minute break and then we'll get back to it.